So welcome you to this module. So if you recall, in the last module, we were discussing various properties of a maximum likelihood estimator. The purpose is finally to study asymptotic properties of maximum likelihood estimators as the sample size goes to infinity. So the model which we were considering was you have x1, x2, xn, a random sample from a population with PDF f theta x. So they all have a common PDF f theta x, where theta belongs to some subset capital theta, which is a subset of Rk, k-dimensional equilibrium space. So your theta is a vector valued thing. So I consider their joint likelihood function, joint PDF g theta x is the thing, but product I is equal to 1 to n f theta xi, where x is the vector x1, x2, xn, which belongs to, let us say, Rmn. So each of these random vectors are m-dimensional random vectors, and theta belongs to theta. Then we talked about the likelihood function. So if we take this quantity for a fixed observed sample x as a function of theta, we call that as a likelihood function. So Lx theta is defined as g theta x as a function of theta. So this is a function of theta for fixed, for observed sample x. So once a sample has been observed, I consider g theta x as a function of theta. Now note that g theta x in certain sense denotes the likelihood or the probability that your sample x is coming from a population, is coming from a population when true state of nature is theta. So then what you try to do is try to look at that theta which is most likely to have produced the given data which you have observed. So that means this data is most likely to come from that population. So that means maximizing g theta x respect to theta or Lx theta respect to theta makes sense, and we say any such theta which maximizes Lx theta for a fixed x is called maximum likelihood estimate of theta as a vector. Then we realize that sometimes it is easier to maximize log likelihood function, because log function is a increasing function. So whether you maximize Lx theta or its log, they are one and the same thing. The maximizer is going to be the same. So you define Lx theta as log of Lx theta. So you minimize this or minimize this. Then we saw some other justifications for maximizing likelihood function, and that we did under certain assumptions. So we added 3 assumptions. First assumption is that your model is identifiable. So the first assumption is if f theta 1x is same as f theta 2x for every x, that should imply that theta 1 is same as theta 2. So that means by these PDFs, f thetas are identifiable, or this g theta is identifiable. Second assumption, we assumed that the support of g theta x does not depend on theta. It is same for all thetas. So g theta x, support of g theta x does not depend on theta. Now you know what is the definition of a support. A point x0 is said to be in a support of a distribution if you take any neighborhood around x, the probability of that neighborhood would be positive. So the probability that your observation will fall in that neighborhood should be positive for any neighborhood around x0. In that case, x0 will be said to be in the support of distribution. For example, in uniform 0, 1, the support is the closed interval 0 to 1, because if you look at 0, if you take any neighborhood, however small it is, the probability of that neighborhood is going to be positive. And in fact, one can prove that support is always a closed set. The third assumption which I make is my theta is open. Theta is an open set. Roughly what it means is it contains a k-dimensional rectangle. So my theta is such that it contains a k-dimensional rectangle. Now under these conditions, we saw that it makes sense to maximize the likelihood function because of the following result. What does that result say? Suppose A1 and A2 hold, then for every theta not equal to theta naught, E theta naught of Lx theta naught is always strictly greater than E theta naught of Lx theta. So what it says is, if theta naught is the true value, then the likelihood function of x, likelihood function at theta naught is always bigger than the expected value of likelihood function at any other point theta. So this in certain sense suggests that if theta naught is the true value, then Lx theta would be maximized in certain sense in terms of expected value at theta is equal to theta naught. Second, for theta naught equal to theta naught, limit n going to infinity of probability theta naught, that Lx theta naught is greater than Lx theta. This would be 1. So that means as the sample size becomes larger and large, if theta naught is the true value of the parameter, then the likelihood function of theta naught would always be greater than or equal to likelihood function of at any point theta. So this provides the motivation for maximizing the likelihood function. So one can find the maximum likelihood estimators, and we have seen finding maximum likelihood estimator is equivalent to maximizing Lx theta or maximizing the log likelihood function small Lx theta. Now many times this Lx theta would be differentiable, then you use your standard calculus to find the maxima. You put derivatives equal to 0, so you find the critical points. But these critical points may neither belong to maxima nor minima. They may belong to local maxima or local minima. So how to determine that they are local maxima or local minima? Then we had a second derivative test in terms of a Hessian matrix. And especially if theta is an open set and Lx theta is differentiable and bounded, then you know that it would attain its maxima and minima inside theta. So the following results tell you how to identify MLE in certain situations. So suppose assumptions A1 to A3 hold. So what I'm assuming is those assumptions A1 to A3 hold, which says my model is identifiable, number one. Second thing is my support does not depend on theta, and theta is an open set. And that for almost all values of x, f theta x is differentiable function of actually what you need is that the partial derivative exists, f theta x. If that is the case, then critical points you can find it out. Now the only thing is, what is the guarantee that those critical points would be the local maximum? Then it says then there exists a sequence theta n hat star of x such that A, you can remove x over here because theta n hat star, which is a function of sample observation, such that limit n going to infinity, that theta n hat star x is a critical point, that probability is 1 as sample size goes to infinity. So p theta naught, theta n hat star x. So this probability with respect to x, distribution of x, theta n hat star x is a critical point, or theta n hat x is a root of Lx prime theta is equal to 0, that is 1. So there will always exist a sequence theta n hat star x such that in limit n going to infinity, probability that theta n hat star is a root of this, that probability would be 1. Second thing is probability that this theta n hat star x is a local maxima, that probability is also 1. So p theta naught in limit n going to infinity, theta n hat star x is a local maxima of Lx theta. This is equal to 1. Third thing is theta n hat x goes in probability to theta naught almost surely with respect to the PD of g theta naught. So note that this equation, this result has very nice implication. First thing is if your equation has a multiple roots, likelihood equation has a multiple roots, then it says there will always exist a sequence theta n hat star x such that limit n going to infinity probability that theta naught at theta x as a root of this is 1. So existence of a critical point in an asymptotic sense is always guaranteed. That is what it is saying, part A. Second thing is saying not only that, such a sequence would correspond to a local maxima as n goes to infinity. As sample size become larger and larger, probability that theta n hat star x is a local maxima, that probability is 1. Not only that, such a sequence would be consistent. As n goes to infinity, theta n hat x goes in probability to theta naught. So one implication of this could be in situations where your likelihood equation has a unique root for every n and x. So if for every n and x, theta n hat star x is the unique root, then what it says? Then theta n hat star x would be a local maxima. Not only that, theta n hat star would also be consistent. So if you see a likelihood equation, it is differentiable, theta is open, support does not depend on theta, critical point, putting critical point is equal to 0, will give you the maximum likelihood estimator, provided the likelihood equation has a unique root. And that is the reason why you must have seen in your bachelor's course, whenever you found out maximum likelihood estimator, you only put critical point is equal to 0, and if the solution is unique, you directly concluded that your solution is the maximum likelihood estimator. It is only in the case where you have multiple roots of a likelihood equation, there could be issues. Then you have to identify which one gives you the global maximum. Now what I'll do is, this result is slightly technical in nature, especially its proof. So I'll try to give an outline of the proof of this result. So here theta is open is an important assumption. The fact that theta is an open set, that is an important assumption. If theta is not an open set, then this result may not hold. So let us try to see that, how to prove it, or at least try to give an outline of the proof. So your theta naught is the true value belongs to theta, right? Theta is open. What does that mean? So what I do is I fix epsilon greater than 0. theta naught is open, so what does that mean? That means I can find a neighborhood around theta naught which is totally contained in theta. So that means theta naught minus epsilon upon. First, let me choose so fix epsilon greater than 0. Then what does that mean? My theta is open and theta naught belongs to theta. This implies that I can find a neighborhood around theta naught which is totally contained in theta. So that means there exists a m naught such that m naught is an integer such that theta naught minus 1 upon m naught to theta naught plus 1 upon m naught is contained in theta. If that is the case, this would imply that theta naught minus 1 upon m to theta naught plus 1 upon m which would be contained in theta naught minus 1 upon m naught and theta naught plus 1 upon m naught, which would be contained in theta, provided this is totally contained in this. This would be totally contained in this if m is greater than or equal to m naught. If m is greater than or equal to m naught, you can see that this set is contained in this. So for every m greater than or equal to m naught. So there exists m naught such that this happens. So what I do is I define R, M, N as collection of all those x belonging to Rn. So I am proving the result for the case where theta is a real parameter. One can have this as a general for general k dimensions, but let me prove it for one dimension. So that x is in Rn. So x is x1, x2, xn. Each xi is a real variable. So collection of all those x belonging to Rn such that Lx theta naught is greater than Lx theta naught minus 1 upon m, as well as Lx theta naught is greater than Lx theta naught plus 1 upon m. So it depends on m and n. Now, if I consider the interval theta naught minus 1 upon m, so theta naught plus 1 upon m is a closed and rounded interval, and your Lx theta is continuous. So Lx theta is continuous on theta naught minus 1 by m to theta naught plus 1 by m. So if x is belonging to Rn, then you know that theta naught minus 1 by m or theta naught plus 1 by m do not give you a maxima, because at theta naught plus 1 by m the likelihood function is smaller than theta naught, and at theta naught minus 1 by m also the value is smaller than that at theta naught. And Lx theta is continuous on this, so it will attain its maximum over here, maximum and minimum both. But maximum cannot be on theta naught minus 1 by m and theta naught plus 1 by m because of this, provided x belongs to Rmn. So I fix x belonging to Rmn. Then Lx theta is continuous on this. So by virtue of 1, let me call this as 1, Lx theta achieves its maximum inside theta. So what does that mean? That is, there exists a theta hat. Now, if it is the maximum, then, and the maximum is in the interior, then you know that it has to be a critical point. So that means there exists a theta hat Mnx such that Lx prime theta hat Mnx is 0. Simple argument. Okay. So I can, without loss of generality, I can we take 1 by m to be less than epsilon. 1 by m naught to be less than epsilon. Why? Because m naught is large enough. I am choosing m naught because this is happening for every m greater than or equal to m naught. So I can choose m large enough so that 1 upon m is always, 1 upon m naught is less than epsilon. So if that is the case, then I try to look at p theta naught mod of theta hat mn x minus theta naught is less than epsilon. So I'll try to show that this always goes to 1. This would always be greater than or equal to p of theta naught mod of theta hat mn x minus theta naught is less than 1 by m. Why? Because if it is less than 1 by m and 1 by m is less than epsilon, so this would imply that this quantity is less than epsilon. So that is why probability of this would be less than or equal to probability of this. And this would happen for every m greater than or equal to n. So then 1 by m is less than epsilon for every m greater than or equal to m naught. Because I have chosen m naught such that 1 upon m naught is less than epsilon. So this is the thing which is happening. But you know that if x belongs to Rmn, then this theta hat mn lies in the interval. So this there exists a theta hat mn. This has to be in the interior of this interval. So theta hat mn belongs to theta naught minus 1 by m with theta naught plus 1 by m. So that means this probability is less than epsilon would always be greater than or equal to, because x belongs to Rmn implies this. So probability that x belongs to Rmn would be less than or equal to probability of this. So, or in other words, probability of this would always be greater than or equal to p theta naught of x belongs to Rmn. But what is the probability of x belonging to Rmn? P theta naught of x belonging to Rmn is same as probability of this intersection. But you know that probability of A intersection B is always greater than or equal to probability of A plus probability of B minus 1. So first you write down this is same as P theta naught of Lx theta naught is greater than Lx theta naught minus 1 by m, and Lx theta naught is greater than Lx theta naught plus 1 by m. And you know that probability of A intersection B is always greater than or equal to probability of A plus probability of B minus 1. So this is always greater than or equal to probability of theta naught. Lx theta naught is greater than Lx theta naught minus 1 by m plus P under theta naught Lx theta naught is greater than Lx theta naught plus 1 by m minus 1. But now just recall the result which I did yesterday. If theta naught is the true value, then you know that likelihood function at theta naught would be the maximum. So know that as n goes to infinity. So from the result which I did yesterday, as n goes to infinity, this probability goes to 1. This probability also goes to 1 for every theta naught equal to theta naught. Yesterday I proved that limit n going to infinity, probability theta naught, Lx theta naught is greater than Lx theta. is 1 in limit, p theta naught, Lx theta naught is greater than theta, again is greater than 1. So this is goes to 1, this is goes to 1, this is minus, so 1 plus 1 minus 1. So this would always go to 1. So p theta naught x belonging to Rmn in limit goes to something which is greater than or equal to 1. So what does that mean? This implies that limit n going to infinity p theta naught of x belonging to Rmn is 1. Now if I do it, let me call this as 2. I apply in 2. So 2 says that, so limit n going to infinity would be greater than or equal to limit n going to infinity of this, but this I have shown is 1. So n probability cannot be greater than 1 in limit, so p theta naught mod of theta hat mnx minus theta naught is less than epsilon is equal to 1. So I have a sequence theta hat mn, but the only issue over here is this m depends on my epsilon, because m naught depends on epsilon. So this happens for every m greater than or equal to m naught, but m naught depends on epsilon, so this sequence will not do it. So I'll have to abstract some sequence from here. But m depends, and hence theta hat mn depends on epsilon. Whereas for showing consistency, I have to show that I have to find estimator independent of this epsilon. But that is not an issue. These all are inside the interval theta naught minus 1 by m to theta naught plus 1 by m. So what I do is fix x belonging to Rmn, which is the set, and define mnx as infimum of all the distances m greater than or equal to m naught of theta hat mn x minus theta naught. So it is kind of a, among all the theta mn at, which is the closest to theta naught, that is what I am trying to look at. Infimum over all m greater than or equal to m naught, theta hat mn x minus theta naught. So the shortest distance I am trying to look at. And trying to identify what would be the corresponding m over here. And that would be the corresponding sequence. But before that, I have to so infimum over all those m belonging to mn. And this anyway is happening over here, Lx prime theta hat mn. So I look at smallest among them. Now note that these distances are always greater than or equal to 0. So this set as such is bounded below by 0. So the greatest lower bound would always exist. So mnx would always exist. Not only that, if your mnx exists, you can find a sequence here which converges to the infimum. So you can find a sequence over here which is equivalent to identifying the sequence of theta hat kns, because these are the distances. If distances are identified, the corresponding theta hat kn is also satisfied. And so clearly mnx exists because this set is bounded below, and anything which is bounded below would have an infimum. So mnx exists, and there exists a sequence theta, let me call that as theta tilde kn, k greater than or equal to m naught, such that Lx prime theta tilde kn is 0, and mnx is the limit of the distance of theta hat kns from theta naught. And so what I do is I take my theta n hat star x as a limit of these theta k n hat x. So let theta n star, theta hat n star x as limit k going to infinity of theta tilde k n x. And this is the required sequence which we are talking about. How? I can, so that, let us look at what is the probability that theta naught mod of theta n hat x minus theta naught is less than epsilon, which is same as p theta naught limit k going to infinity, because theta n at star x is same as limit k going to infinity theta tilde which is same as, by definition of theta hat kns, theta hat kns minus theta naught in limit is same as mnx, which is same as probability that mnx is less than epsilon. Now, you know that probability that x belongs to Rmn is 1. And for any x belonging to Rmn, mnx is this. So mnx is less than epsilon, that means infimum is less than epsilon. But for each of them, this happens. So for infimum also it would happen. So this would go to 1 by virtue of by 2. And by fact that limit n going to by 2 and the fact that limit n going to infinity of probability that x belonging to Rmn is 1. So that proves that theta hat star x is consistent. It is a critical point that will, so also for any x belonging to Rn, Lx prime theta hat kn x is 0, right? Because that is what we had chosen. These are the point of local maxima inside that interval theta naught minus 1 by m to theta naught plus 1 by m. So what does that mean? So limit k going to, because this happens for every k, get n going to m naught, so that means limit k going to infinity of Lx prime theta hat knx is 0. Now note that Lx prime is derivative. A derivative cannot have a discontinuity of the second kind. Or in other words, if for a derivative limit x going to p plus and limit x going to p minus exist, then derivative will be continuous. Here I know that limit exists and this is 0, so it has to be continuous. So this implies that Lx prime limit k going to infinity of theta hat knx is equal to 0. Why? Derivative cannot have discontinuity of second kind. Or in other words, if for a derivative left hand limit and right hand limit exists, then the derivative would always be continuous. That is a well-known property from your calculus, which implies that Lx prime theta hat n star x is equal to 0. So that means for every x belonging to Rn this happens. So that means probability that Lx prime theta hat n star x equal to 0 would be greater than or equal to probability that x belongs to Rmn, and which is, as n goes to infinity, goes to 1. And that proves the result. So one immediate conclusion of last result is that in case of multiple roots of Lx prime theta is equal to 0, the above theorem says that there would be a one sequence which would be consistent, which asymptotically as n goes to infinity would be a local maxima. So then one has to look at various local maxima and one has to identify which one is the global one. But in the case where Lx prime theta is equal to 0 has a unique solution for every n and x, the last theorem says it would be MLE and it would be consistent. So these inferences we'll draw next time. So for this module, I would stop here. We'll discuss the consequences of this result in the next module. Thank you very much.